Log on, tune in, find out. Another good idea from Cambridge.
This afternoon is Prof. Simpson, who's talking on Moduli of local systems on Deligne-Mumford stacks.
Okay, so thanks very much for this, for inviting me to give a talk. Also, it's a pleasure to be here at the Newton Institute, which is very convivial and nice. Okay, so I'd like to talk about sort of a little extension of the theory of moduli of local systems. Which is, the non-abelian Hodge theory. Which is mainly the Hitchin correspondence. Plus all of the extra structure. To the case, so it can be extended to lots of different things, but so what I'd like to say is that it can be extended to the case of let's say smooth proper Deligne-Mumford stacks. Then let me put this in quotes, but fairly easily. And sort of the advantage of this point of view, well, one advantage at least is that it allows us to discuss some kinds of local systems on open varieties. Without too much trouble. By too much trouble, I mostly mean, Takuro Mochizuki's gigantic theory for open varieties, which is not very easy to work with. Which is not to say that it's just, that's the real thing you should be doing, I think, but to sort of shortcut that and, be able to say stuff a little bit more easily, you can sort of replace that in some cases by the case of DM stacks, but also also we get some new kinds of examples. And in general, it seems to be a good source of things which may be a good source of cases which may be easier to compute. If you take, if you look at local systems on a smooth curve of genus G, if you take rank 2 local systems on a curve of genus 2, it already has dimension 6, and it sort of goes up from there. So to get stuff of smaller dimension, you need to go to something either open varieties or Deligne-Mumford stacks. So I'll try to explain that. Well, let me just start off by explaining something about basic definition of how does this work? Of Deligne-Mumford stacks. Okay. So Deligne-Mumford stacks, from the point of view of what we're doing here, it's pretty much the same to talk about orbifolds. Or in the title of the preprint, I put V manifolds. I'll explain that there, you know, the Deligne-Mumford stack case is just a teeny bit more general than the classical definitions, which I'll explain in a minute. Okay, so what's an orbifold or a Deligne-Mumford stack or a V-manifold? So the basic idea is that it's like a variety, but where the local charts can, let's say, be glued to themselves by automorphism. You know, a variety is made up by gluing together local charts, by gluing, but you glue one chart to another. Okay, what happens if you happen to take a chart and try to glue it to itself by an automorphism? That's what you get. I mean, that comes out clearly in the original definition of V-manifold, for example. So let me just say what, you know, the basic example here, and pretty much a good example for lots of applications too. So the case of dimension 1. So suppose that, so let's look at dimension 1. Smooth proper. So let's call these DM curves if it's dimension 1. Okay. So in a sense, which I'll explain in a minute, a DM stack has a group called the generic stabilizer. And let's assume that that's 1 for now. So if we assume that, so we look at, you know, dimension 1 smooth proper DM curves with trivial generic stabilizer, then they're just classified as follows. Then these are the same as thing. Okay, these are. And I'll give the notation. These are all of the form x is equal to some y, and then so we'll give this notation here. So this is what's called a root stack, where y is a smooth curve. I'm working over C here, okay. Y is a smooth proper curve, and y1 to yk are points, okay. And the ni are integers greater than or equal to 2. Okay. Of course, if you put n, you could put ni equal to 1, but then that would not have any effect, so let's not do that. Now what does this mean? Okay, the local chart for x, and let me just say that this has a map to y. Okay. A local chart for x over a neighborhood of the point yi in y is of the form, is a disk with coordinate t such that t to the ni is equal to u, where u is the local coordinate for y at the point yi. Okay. So we're just talking about a ramified cover, basically. So we have this disk, whatever. So this is a disk, but it maps by a double ramified cover to to the disk inside Y. If n equals 2, for example. So this is, in general, an ni to 1 ramified cover. Okay? And the group acting on the local chart here is let's see. In fact, let's call this delta. Delta modulo the group the local piece of X, of the Deligne-Mumford stack X, is what's called the stack quotient of the disk divided by the group cyclic group of order ni, which is operating by t goes to t goes to mu times t. Where mu is nth roots of unity. Maybe you could put ui here, that would be better. Okay. So just divide the disk out by rotations by roots of unity. And of course the fixed point, the origin is a fixed point. And so from this example we can see something important for what will follow, which is that, okay, let's let u equal y minus the points. And of course, over u, the local charts are just the identities between x and y. So it's also a subset of x. Okay. So we're going to have pi 1 of u. Let's choose a base point. Mapping into pi 1 of x. Well, let's call this x. Well, I haven't told you what this is, but okay, this is sort of a definition in this case. Okay. And the definition is that pi 1 of x is defined to be pi 1 of u modulo the relations gamma I to the ni equal 1. Which is to say, if downstairs here, okay, so what's gamma I? Gamma I is the path in y which goes around the point yi. Okay. So it says that if you go around once here, if you try to go around once, when you lift that here, that won't actually lift to a path in the chart. But if you go around ni times, then that lifts to a path in the chart, which can then be contracted. And so local systems on X are the same thing as local systems on U, let's call them L, with finite monodromy of order ni around yi. Okay. Just representations. So a representation of this group is the same as a representation of pi 1 of u, such that the monodromy element goes to something of order ni. Okay, so this is the basic example. Now, how can you make a general definition which sort of covers this basic example? Well, so the sort of the next kind of more general basic example is suppose phi is a finite group acting on a variety, let's say smooth variety Z, then we can form the stack quotient Z modulo phi. And a good example is the case where, is in this case. Okay? So, in the previous example, if Z mapping to Y is a phi Galois cover, with ramification of order Ni, by which I mean ramification which locally looks like this guy, then the stack quotient is equal to this Deligne-Mumford stack X, which we discussed here. And more generally, the stack quotient is just take the local charts of Z and use the elements of the group phi to define the gluing functions. And of course, you get a stacky point exactly when you have a local chart, which is a local chart near a point which has a stabilizer. Then the stabilizer group of the point will act by automorphisms of that chart. Okay, so that's the case where you get a chart which gets glued to itself. Okay. So now this example lets us go towards the basic definition, which is, so we have a map from Z into X, and X is sort of the quotient of Z by some relation. Okay, but now what happens in this example, but what if phi acts trivially? If phi acts trivially, then the quotient is, let's see, then X is actually just the same as Z cross a stack called B phi, where B phi is just the point quotiented out by phi. So this is sort of the new kind of thing which can happen here. Now, what I wanted to say is just that it's new in a certain sense, right? Because we haven't really defined this, but in fact, it's also not new in the sense that what happens if this guy actually occurs up here. So, in the previous example, we have a B of Z modulo Ni is a substack of X, which is Y of, it's a substack of this root stack located at the point Yi. Okay? And so in general, if you try to say, okay, let's only look at group actions which are faithful, but if you take a faithful group action but then restrict to a subvariety which has a stabilizer, for say the fixed point set of the group action, then of course the group action will no longer be faithful. Okay, so you sort of have to go to the case where the group might not act faithfully, and then this is sort of the opposite case. If the group acts totally non-faithfully, namely trivially, then the stack is just the same variety as Z, but with this thing which is the generic stabilizer group. Okay, and so this is the So with these examples, this is sort of an example approach to the definition plus the basic things which happen. Okay. Now, what's the general definition? Okay, the definition is that it's a one stack in groupoids. On, say, the side of schemes, let's say, of finite type, I guess probably better, over C with the Étale topology. Let's see, call it X, such that there exists a map Z to X, with Z being a scheme. Let's, I'm just taking finite type things, so it's scheme of finite type. And such that the relation, so that what's the relation? So R is Z cross X Z. So let's see, we want this to be a Étale map. So you have to define what an Étale map means, but that's pretty much the same as what I'm about to say here. This guy, the two different maps from here to Z are Étale. Is this supposed to be representable map? Maybe. Sorry, right, representable means that an Étale map of schemes. Or to put it another way, it's a stack with the property that there exists a presentation like this, so that X is Z modulo the relation R. Okay. Now, R here is actually a groupoid in the category of schemes. I mean, R is the morphism object for a groupoid, and Z is the object for a groupoid. I'm probably getting that still wrong, but and then X is separated if R mapping to Z cross Z is proper. And proper if any I won't write this down, but any, because this is supposed to be a discrete valuation ring and this is the fraction field, any map into here extends to a map spec A prime into X. Where this guy is a finite extension. So this is the classical separated evaluative criteria of properness, except you have to be a little bit careful because, as you can see from the example with the disk there, if you have a map from a punctured disk into X, for example, this punctured disk here, if you take out the origin, away from the point, X and Y are the same. So you can have a map from the punctured disk into X, but it's not going to extend to a map from the disk into X. It's just going to extend once you go to a finite cover. Okay, and then there's a theorem of, this is equivalent to saying that there exists a proper map, a surjective map. Where Z is, let's say, a proper scheme. Now, so the sort of basic properties. I think that for me, the main basic property which sort of lets you understand what's going on is that says that this example is pretty much the general example, this example here. So if you have x is a separated finite type, I won't write finite type because everything is finite type here. If x is a separated finite type DM stack, then it has a coarse moduli space. X coarse with a map from X to it. And X coarse is an algebraic space, a separated algebraic space. And locally, I won't say, this kind of has a universal categorical quotient property. Okay. To sort of define what it is uniquely. And locally over the coarse moduli space in the Untitled topology, I think this might even be true in the Zariski topology, but maybe we need to be careful because it's an algebraic space. So let's say in the locally over X coarse in the Untitled topology, X is a quotient stack, which is to say there exists there exists a map, an Untitled map from U to X coarse such that X cross over X coarse U is of the form Z divided by a group action, by a finite group action. So this means that in fact you can choose charts for the Deligne-Mumford stack which really are the quotient by a group. Whereas a priori it's just, by the definition, it's just a quotient by a groupoid. And sort of a furthermore here, in the case of curves, it's almost always in the case of smooth DM curves, it's almost always a global quotient. I think the only examples, maybe I'm missing one, but I think basically the only counterexamples, the only other cases are things which people call drops. So a drop is something like that. So it's a P1 with 1 point, or footballs. This is American terminology, okay? I guess I should, I don't know what's a rugby ball called, but whatever. P1 with 2 points, okay? And in fact, okay, even if you take P1 with 2 points, if the orders are the same, then of course that will be a quotient by P1 by just a cyclic group action. So say P1 with 2 points with relatively prime orders. And in fact, in these cases, the fundamental group is trivial anyway, so you can more or less say that for the cases where we want to look at the fundamental group, you can just assume that, and if you're looking at a curve, you can pretty much always assume that it's a global quotient. Let's see, now what happens, what happens if you take, what happens to pi 1 if you take, well, first let me just say the definition of pi 1. So, if we have a stack, if we have a DM stack, then let's call this Z modulo R. So we have Z mapping to X, and R is Z cross XZ. I guess what I didn't say here, when we say Z mapping to X, of course, Z is considered as a sheaf of sets on the site of schemes, wherever that is. maybe I just erased it. Okay. Anyway, yeah, here. Z is considered as a sheaf of sets on this site, which a set is a discrete groupoid. Okay, so they're all living in the same world, and then we have a map. And the fiber product is a fiber product of stacks of groupoids. So that means that an object of the fiber product is a pair of points in Z plus an isomorphism in the stack. So R is really the scheme of isomorphism. So now if we've got all this, then we can form a simplicial scheme by taking Z0 equals Z, Z1 equals R, and Z2 is Z cross X, Z 3 times, etc. Well, let's just call this Z dot. And then we get a simplicial space Z dot top by taking the complex topological space, and then we get a simplicial set, which is this for each. Let's see. For each integer k, we associate the singular simplicial set of the topological space Zk, which is a bisimplicial set. And then we take the diagonal to get a simplicial set, and then realize to get a topological space. Okay, so I wrote everything down. How to go from a DM stack to a topological space. Okay. You can do other things which are equivalent to that. I mean, you should do something which is homotopy equivalent to that. Okay. So this gives you the realization of X. Okay. So we can define the topological realization. Of X, and so it has, so say pi 1 of X is equal to pi 1 of the realization of X. If you have a point of X, then you get a point inside here, okay, so on, etc. And local systems on X are by definition local systems on the realization of X. Now, there's other ways of approaching this which are useful. And in particular, there's a paper, or maybe a series of papers by Nui. Notably, you can think of a loop in X as a collection of segments in Z whose endpoints are joined by elements of the relation scheme. I mean, if you have a loop in X, you can think of lifting it to a loop in Z, but you might not be able to lift it completely to a loop in Z, but you can sort of lift it segment by segment. In fact, I think you can really go all the way around, but then you might get to the wrong point, basically. So you can define the pi1 more explicitly that way. And then you have to see that, for example, in the case of a curve, that gives back what I said before. Let's see. Right, so what was I going to say? So if x equals z quotiented by phi, so then we have a map from z to x, and we also actually have a map from x to b phi. That's a little bit harder to see, but z maps to just a point, okay, so we can take the stack quotient of the point, which is b phi. And this is actually a fiber sequence. The fiber product of this stack with the point mapping to here is actually x. So we get an exact sequence. That's right. Sorry. Z, this is x, and z is the fiber. Okay. So, and let's lift the base point up to z. So the fundamental group of the stack is an extension of the fundamental group of the upstairs guy by the group phi. You can do some other exact sequences. Maybe I won't write this down for lack of time, but for example, in the curve case, when I said, that we can classify DM curves as being just root stacks, that was under the hypothesis that the generic stabilizer is trivial. If the generic stabilizer is not trivial, then you get a gerb. Okay, I should say what's a gerb. Maybe I'll say this. Okay, so in general, for a DM, so the form x mapping to y, let's see, x mapping to, let's call this maybe x prime. And the fiber is a sort of a b phi. So this is a gerb. There's a group. This group is the generic stabilizer. So it's a phi gerb over a root stack. And then you can also do an exact sequence of fundamental groups for that guy. So you can pretty explicitly say what the fundamental groups are. Okay, now the good basic example in higher dimensions is again a root stack. So I'm not going to say I'm not quite sure what the exact right generality to define this is, but let's just suppose d equals d1 plus dk is a strict normal crossings divisor. So these guys are smooth and they intersect normally and so on. Then we can define inside in a smooth variety y, then we can define again x equals y d1 over n1 dk over nk. And here again, the local charts so I'll give a local chart, say, at a point where they all intersect. So if we have local coordinates Of course, if you have only some of the divisors, then you just take some of the coordinates. If you have local coordinates defining the di, then locally the chart Z is just the set of points, is the subvariety of y cross a1 to the k. Given by ti to the ni equals ui. In fact, it's just the product of the one-dimensional root stacks. And the group equals the product of these cyclic group acts. And x locally is the quotient. And those are good examples of stacks. I mean, they're perhaps the most useful one. And here again, well, maybe I not write this down again, but this explains the what I was saying about the application to open varieties. Okay, if we take u equals y minus d, then pi 1 of x is equal to pi 1 of u, modulo, again, the relations which are gamma I to the ni equals 1. So local systems on x are the same thing as local systems on u with finite order monodromy around the divisor components at infinity. And also z is smooth. Here's a little glitch. I mean, here's a little thing which you have a little remark that you should notice, which is that it's not a good idea if you have a normal crossings divisor. It's not, I mean, a good idea. I mean, it doesn't work out quite as well if you try to take the root stack of the full divisor d, because there you'll get something singular. So you want to sort of take each component and take the ramified cover of each component separately. If you just take an n-fold ramified cover along d, then you'll get some kind of conical singularity at the crossing point. So this roughly speaking corresponds to a map from the pi 1 of the complement of the divisors locally is a product of copies of z. And here this maps to this group. If you map that to just a single z mod n, then the chart is no longer smooth. I mean, you can do that too if you want, but you don't get it smooth. Okay, so now what do I want to say about this? It's just that we have a lemma smooth. If X is a smooth separated proper DM stack, then there exists a map from Z to X where Z is a smooth projective variety. Not necessarily connected. Where Z is a smooth projective variety, and if Z prime contained in Z is the open set where F is étal, then Z prime covers X. Okay. So of course you can usually not get a case where you have an étal map from a smooth projective variety. That would be the case of a global quotient of a smooth variety by a group, but that's usually not the case. But you can get the case where you have a projective variety and it has an open set where F is étal, and that open set covers X. So for this, this uses a basically uses the result by Raynaud-Peskin, which allows you to blow up. If you have a algebraic space, it allows you to blow it up if you have an algebraic space with a quasi-projective variety inside it, you can blow it up to resolve singularities and make it become projective by staying away from the sub-guy. That's what allows you to get surjectivity here. You can modify it. You can take your chart, sort of complete it in some way. Or you can take, the original charts were open. Okay? You sort of complete them in some way so that it maps to X, and then blow up in such a way that it becomes projective, and then use a root stack to make sure it actually maps to X. Okay, now what can we do with this? Okay, using this, we can make a resolution by smooth projective varieties. So let's take Z0 equals Z. Then let's take Z1. Let's take it mapping to Z cross X Z. Okay, this is just, again, a smooth, I guess, algebraic space proper. But again, we can choose a smooth projective variety which maps surjectively to here. And then continue in that way. To continue here, you just sort of apply Deligne's procedure. So from basically, this is included here. Here we're just applying the procedure in Deligne's Hodge 3 paper. Okay. And then now let's just do some notation here. So eta is going to be some kind of local system. So either there's, different notational schemes, but Bilbao or Hitchin, or Durham, or Betty, or we can maybe call this Hodge, which is contains these lambda connections, or Deligne-Hitchin. So this is the twistor space. And then we have M eta of X G. So let's say G is some group. So I'll take a complex group. So in some cases, I guess you can do a real group, but I'm not saying anything about that. Complex, say, reductive group. I'm usually thinking of GLN here, so if I say something that's not true for G, but only true for GLN, that's possible too. So this is the moduli stack of eta-type local systems. On X. And the point is that you can just extend, this extends to the case of X, a Deligne-Mumford stack. By setting M equals the 2, let's say, limit, I guess. The 2 limit of the diagram and in fact, since these guys are 1 stacks, it suffices to go up to M2 here, to Z2. what does this really mean? So an object here is just a local system here plus an isomorphism phi here, such that, say, P1, let's say P01 star phi, maybe I'm messing up the order here, P1 2 star of phi should be equal to P02 star of phi. So once you have once you have that, once you have a simplicial scheme resolving your guy, then you can just define the moduli space of local systems. So I mean, this is, it's a theorem that this is true if you take the Betti case. Betti being just real topological local systems. So the stack of local systems on the Deligne-Mumford stack, which in that case means representations of pi 1 of the topological realization, that is the two limit of the stacks of local systems on the pieces. And then you can just sort of take that as the definition for all the other guys. And now actually to do that, you didn't really need to use this lemma because you could have just taken any smooth projective variety mapping to X by a surjective map. Okay. And sort of cohomological descent kind of tells you that that's going to calculate the homotopy type of X. But I guess, I mean, I'm not 100% sure that there's actually any need for this lemma, but I mean, it does seem to make it a little bit more transparent, the fact that, in fact, if we take, say Higgs bundles on X, are by definition then Higgs bundles on Z dot, so meaning one of these guys. And here we're including the conditions semi-stable and the Chern classes are 0. But in fact, those are can also be seen as really, vector bundles plus theta and so on the DM stack X. Because of the fact that I mean, this guy is not really a covering of X. It augments towards X. It's not really a étale covering of X because it's only étale over some open set. But if you restrict your guy to this Z prime, then it does give you something with descent data down to X. So you really get a bundle on X. Let's see. Now let me just make a remark here, which is that, so we can define this, the category of Higgs bundles defined in this way becomes the same as the category of Higgs bundles on X, but we have to define semi-stability on X is defined to be that E theta restricted to any curve for C, a smooth projective curve. Because the point is that we're working here in the case of a proper DM stack, so we're not actually assuming that it has any property of being projective. In fact, I mean, it's a priori not even clear what it means for a DM stack to be projective. Okay. Now, you can imagine a couple of different definitions. You can imagine, okay, let's say that the coarse moduli space is projective. Then there's also a guy, I think his name is Neroni. Maybe.
Yes.
Yeah, who has a definition of.
The definition is not his, actually. The definition he got from a paper of Andrew Crash.
Okay.
And he uses the projectivity of Andrew to define.
Okay, so they have some notion of projectivity, which is more complicated. And so I'm not quite sure. So you can probably make that work and define some kind of semi-stability and so on. Which I think is an interesting question because that lets you look at vector bundles, say with with Chern class is different from 0. But if you're looking at things with semi-stable with Chern class is equal to 0, then semi-stability is supposed to be independent of the choice of the polarization, and is equivalent to just saying semi-stable when you restrict to any curve. Okay. This is sort of strong, maybe let's see, pluri-semi-stable or something like that, you might call that. Well, I'm running out of time here, but so that's just to say that you can kind of do the theory, the whole local system theory, in this case, and you sort of get it for free, essentially for free. Okay, you have to play around a little bit with this case of the simplicial scheme, and so if you want to rigidify things by choosing base points, then you have to be a little careful about how you choose the base points. And notably, you should start off by choosing a lot of base points so that you get base points in all the different connected components of everything here. Then you have to analyze a little bit what happens when you try to, take out those base points one by one and try to get back down to a moduli stack, and then, you can, by doing that, you can prove that the moduli stack has a universal categorical quotient, which is a moduli space, whose points are reductive representations. Okay. And then, all the basic properties still hold. So, for example, this is hyperkähler on the smooth points. And you have the M. You have the Riemann-Hilbert correspondence, the Hitchin correspondence, and so on. Okay. And that all just kind of works by, saying that it works on the simplicial scheme. I forgot to, yeah. Let's see, so, yeah. Now what I just wanted to say, to finish here, is that, okay, so this up till now the theory was, just everything works the same way. So now in what sense do you get something new here? So new phenomenon. I guess for those of you who are going to the conference in 2 weeks, I'll be discussing this case a little bit more. But so for example, so if y equals p1 and x is equal to y so x is a root stack over p1. Okay, so local systems, so m mx gln can also be thought of some kind of parabolic local systems or whatever. So in the case in particular for the case of parabolic Higgs bundle, okay, so moduli, in fact, strongly parabolic. Higgs bundle. Then the moduli space decomposes in a disjoint union of components corresponding to the conjugacy classes of the, so in this case it's the order finite order local monodromy. Okay, so the local monodromy transformations have finite order, so their eigenvalues are roots of unity. Then you can say, what's the multiplicity of each eigenvalue? That determines the conjugacy class. And that, so you get a disjoint union of spaces depending on the choice of conjugacy classes. And for some choices of conjugacy classes, there exists no parabolic. I guess I'm skipping over something here, which is that there's a correspondence between local systems bundles or whatever on the root stack and vector bundles on Y with parabolic structure at the points. Okay. So for some choices of conjugacy classes, there exists no parabolic stable or even semi-stable bundles. Which is to say that in terms of DM stacks, there exists no stable, semi-stable vector bundles. on the stack X with those local conjugacy classes. In fact, when you have a vector bundle on X, you also get it's no longer a monodromy transformation, but you get an action of the finite group on the fiber of the vector bundle. So you can again decompose that way. And so this is a case where the phenomenon that we saw on, I guess that was Tuesday, right? It no longer holds. So that the minimum of the Hitchin functional. So for these components of the moduli spaces, the minimum of the Hitchin functional consists of things consists of Higgs bundles with theta different from 0. The phenomenon where on a compact curve where you say if you have a minimum of Hitchin functional, then the theta has to be equal to 0. So even for GLN, C. In this case, can no longer be true depending on the weights. I guess probably always will be some weights for which there do exist stable bundles. In that case, the minimum will be the stable bundle. But there exist some components in this case where the minima have theta different from 0. Let's see. So that was maybe I'll stop.
Any questions?
These correspondences between the three different moduli spaces, usually you have to do some analysis, right?
Mm-hmm.
Existence of harmonic metric and so on.
Mm-hmm.
So how do you deal with that in this sort of general context? I mean, for the parabolic thing, I understand. I think for these other general situations, what do you do?
Well, that was kind of the point of why I was interested in looking at this whole thing with the simplicial space and so on. Because actually you don't need to do any further analysis here. You can just apply the fact that you know the correspondence over Z, which is a smooth projective variety. And then that just gives you the correspondence over the... and in fact, I think you can get a harmonic metric, in fact, that way, because you have a harmonic metric on Z, and it satisfies the descent. You have a descent cocycle. So let's see. I guess maybe not the metric, but at least the connection, the operators to give a harmonic bundle. Those will be preserved by the cocycle phi, so they'll descend to X. And I mean that's one of the reasons why you would be interested in having a map Z with the property that with the property that z prime surjects onto x, where this is étale. Because if you just kind of chose any old covering in the proper surjective topology, then you wouldn't necessarily be able to get any kind of good object on x that way. But here you can just descend, you can restrict your guy to here and then descend it back down to x. So then, of course, you can ask the question also, could instead of doing that, could I just do the analysis on the Deligne-Mumford stack? So it seems likely that probably should work. You know, you have to have a Kähler metric on the Deligne-Mumford stack, and that seems to make sense. You know, what's the Kähler metric? Even better sense than it is to say what it means to be projective. Because the Kähler metric is just sort of a local analytic thing. But I didn't do that, so.
So you may occasionally mention that this was one stack, and if, for instance, you said, well, here we can stop here because after all, this, do you expect in principle this would work whenever n stacks are alive and running?
Yeah, I think so. I think if you're looking at some kind of non-abelian cohomology n stack, then you should be able to go out to like n plus 1 or n plus 2 or something like that.
So you don't think this has anything specific to do with the fact that there you are stopping at if you have
I don't think so, but okay, you'd want to look at that because we're looking at when we're saying this about the harmonic metrics and so on, we're really using the start of the resolution. And so you can ask. So I think you can ask. What kind of good properties can you get for the rest of the resolution? Which I didn't try to get any good properties. I just said apply the method that you get in Deligne's Hodge 3. Whereas John has a nice thing, which is not on a slightly different topic, which is how to get a nice resolution of a geometric n stack. But maybe those techniques would apply here to get some kind of nicer resolution where you can. Do you have sort of an étale resolution sitting inside your other one?
Won't you need some kind of a resolution of the Kähler identity? I mean, you need the Kähler identity somewhere, right? I mean, you never touch the Kähler identities here.
No, I'm just saying here that since you have the correspondence over z, and it's sort of nicely functorial and everything, that you get it over x. I mean, if you want to take cohomology.
Right. If you want to do an n stack, you have to take cohomology.
No, but I think that's what's happening in Hodge 3 anyway. In fact, one thing I didn't say was that x doesn't really need to be smooth. I mean, it could be singular or even forget about x altogether. You can just take a simplicial scheme basically. A simplicial smooth projective variety, and Deligne's Hodge 3 tells you how to do Hodge theory for that. I guess John Pridham actually has in his paper, in one of his papers, has a section saying you can do non-abelian Hodge theory on a simplicial variety. So I put that in as a reference on the published in the one the paper will be coming out. So I think then. At what point would you really want to be doing some kind of analysis on your Deligne-Mumford stack? I'm not sure about that, but as I said, I didn't actually do that.
So when you study Higgs bundles, but with real reductive Lie group, for example, if it is real maximally split, then you have the Hitching components in which also the minima has non-vanishing fixed field. And these components, it is known that they are extremely relevant from the geometric point of view of the curve. So do you expect these components in
I guess so. I think that would be interesting to look at how that works in these cases. I mean, the interesting case, the interesting first case seems to be this, where you take P1 and take a root stack on P1. I think it would be good to try to understand. I mean, so then there must be something combinatorial going on in the relationship between the monodromy transformations that you're requiring here and the group that you're looking at. Maybe another thing to say is that this parabolic thing only works for the group GLN, and already for other complex groups, there's this whole theory of parahoric structure. which you need to do to get a correspondence between bundles on the stack and principal bundles. So I don't know what kind of extra stuff you need to combine real stuff and parahoric stuff and so on. But yeah, I think. But I'll be talking a little bit more about this in some special case in 2 weeks, and I think that, you know, the set of real points, when the parabolic weights cross a wall, then the set of real points actually get some singularities. So something strange is happening in that case, which I don't quite know what it is, in fact. But yeah.
Any more questions?
I just want to make a comment that actually this, what you just said, for real as well as other complex groups is, you know, taken from your classical and
Even in the parabolic case?
parabolic system.
Ah, okay. Is that come out yet?
I hope so.
But, do you guys have like an archive preprint or something about it?
Not yet.
Okay. Oh, great. Cool.
Okay, so then can we thank the speaker again?